All right, we are on the fourth video. We're looking at nuclear chemistry, and we're going to be looking at half-lives and some of the uses of using radioactive material to then identify age of things. So let's look at what a half-life means, and then we'll look at how to use it to date stuff. All right, so a half-life is, by definition, the time required for an isotope amount to drop to half of its initial amount. All right, so we're taking some initial amount, and then once it divides in half, so let's say 10 grams to 5 grams, the amount of time it took is called its half-life. Different elements or different radioactive isotopes will have different half-lives, and you can see they vary here from very short. Here's iodine 123 is a half-life of 13.1 hours to extremely long. Uranium 235 has a half-life of 7.04 times 10 to the 8 years. So very short to long amount of time that it takes for these to divide by half. And we can make use of that, different ones, to do different types of treatments or to age things. So we're going to just look at an example just to make sure we understand what this idea about half-life is. So suppose a patient's given 30 micrograms of iodine, iodine 123 specifically, and this is used to treat thyroid disease. How much of the iodine will be left in 39.3 hours? So I want you to think, okay, we have up here that this isotope specifically has a half-life of 13.1 hours. And we're asked, well, okay, how about after 39.3 hours? And you should be able to think, well, in 39.3 hours, this will undergo 3 half-lives. Since 39.3 divided by 13.1 equals 3. So it's going to go and cut its amount in half 3 times. We can probably just kind of work this out right here. If we're starting with 30 micrograms in 1 half-life, so this is, I'm going to say T 1/2. So in 1 half-life, it would go down from 30 to 15 micrograms. Another half-life would take it from 15 to 7.5. And we need to get to 3 half-lives, so let's just cut this down one more time. All right, so here goes another 13.1 hours, and now how much is left? 7.5 divided by 2, 3.75 micrograms would be left after 3 half-lives of this iodine isotope. Not too bad. Let's look at a calculation with this. And it's important to kind of know, we actually used this calculation, but you didn't really know it. There we go, it's showing up. So we did actually use this, and just to give you a little heads up, all right, so NT is the amount of radioactive at time T, and O here is the amount that you started with, or the initial amount, and T is the elapsed time, okay, so that's at time T, this is that time, and then T 1/2 is the half-life of that isotope specifically. And I told you we just used that equation, but what we just did looked nothing like this, right? Let's just kind of work out what we just did. We said that, we were trying to solve for T at 39.3 hours, right? So we were trying to solve for NT, that's what I meant to say. We're solving for the amount. And we know that we started with, the initial amount was 30 micrograms. And then we had to figure out, well, how many half-lives did it undergo if it went to 39.3 hours? Did I say years earlier? It's 13.1 hours and 39.3 hours. So let's see. The half-lives, this is how we figured out how many half-lives. It was 39.3 hours is the total time that we had, that we were asked about. And the half-life, the T 1/2, for this specific isotope is 13.1 hours, okay? So this is the same as taking our 30 micrograms, I think I'm doing an extra squiggly there, times 1/2 raised to the 3rd, because we figured out there's 3 half-lives. Once you actually calculate that, you get 3.75 micrograms. And this might be easier to actually use this equation. This would be given to you. You wouldn't have to memorize this. You should just know how to use it. If it's not an exact number of half-lives, like what if it's, 3.235 half-lives are being used. It might be easier to plug it in than trying to solve it. Let's do another example. So you have 63 grams of cobalt-60. I'm going to put a dash there. The half-life of cobalt-60 is 5.27 years. And so the question is, how many grams will be left after 3 years? All right, so if you're starting with 63, you know you're going to have less than 63. That's one thing you can think of. It's going to start decaying, and so you'll have less of it after 3 years. Now, the half-life is 5.27 years, so always do some thinking to yourself. Is this one half-life 3 years? No, it's not even one half-life. It's just over half of a half-life, right? So we know that if at one half-life, 63 divided by 2 would be 31.5 grams. So we know we're somewhere in between. I guess I would say we expect this to be somewhere between what it is at a half-life at 5.27 years, which would be 31.5 grams, to what it is right at the initial time, 63 grams. Now you can't just, you have to kind of now set this up. So let's kind of figure out what it is using the equation above. So NT, the amount at time t at 3 years, is what we are solving for. Our initial amount is 63 grams. And the rest of this we're going to plug in there. 1/2, okay, and then the number of half-lives we're going to get is t, okay, so this is 3 years. And the half-life is 5.27 years. When you're setting up this t to time and a half, I do want to make sure you realize that you should make sure the units cancel out. The previous example, they were both in hours, the time, and the half-life was in hours. Here, they're both in years. It doesn't matter what unit of time they're in, as long as they're the same, so they would cancel out. All right, so plug this into your calculator. And when I did, I solved, I got 42.46 grams. And I think I'm just going to go to, looks like we had 2 sig figs here, so I'm just going to say 42 grams of cobalt-60 remain. So since we knew its half-life, we can then figure out, if we know its starting amount, we can figure out how much of it would be left after a certain amount of time. Let's just make sure we can do and think about half-lives, and then we'll get into using some radioactive dating as well. So this next one, I have a question for you. It's kind of really wordy, so sorry about that. I'm gonna have you pause, kind of read it through, and try to figure out if you can get the answer. So pause, try to read it, and we'll come right back. All right, hopefully you had some time to figure out and read this problem through as well. So you can see this is a strontium isotope, all right, that decays, and this can get into your body. It can get into your bones. It replaces calcium, so you do not want to have too much of this. It has a pretty long half-life. You're told the half-life is 29 years, and so you're asked about how much is going to remain, what percent of it at 58 years. So you had to realize that 58 then is 2 half-lives. So then you take 100%, and that's at the initial. After 1 half-life, you're down to 50%. And then you go 1 more half-life, and you're at 25%. So correct answer there is D. We're going to continue to use this concept of percent left over as we look at carbon-14 dating. All right, so looking at, you probably have heard of using carbon-14 to date objects. And let's look at how carbon-14 is actually produced in the first place. So all of carbon-14 is produced in the upper atmosphere, and this will occur when a neutron bombards a nitrogen atom up in the upper atmosphere. So you can see here that the atomic number goes down to a 6 here, okay, and we have left off a proton is given off here. And then the mass number has stayed the same. So a neutron bombards a nitrogen, and now we have made this isotope carbon-14. Now this gets into the food chain, carbon dioxide, plants, you breathe out carbon dioxide, you get it in your body, you have lots of carbon in your body, and overall, living things will roughly contain a constant amount. All right, so it's in all living things at a constant amount. All right, so you're breathing in, you're letting it out, carbon's coming and going. So it stays relatively the same when you're alive. However, once you are dead, okay, you are not going to be taking in any more carbon. And so now all that carbon-14 that was in your body will start to decay, and no more carbon-14 is coming in. So it now starts this decay process. Carbon-14 has a half-life that's fairly long, 5,715 years. And you can tell me what kind of decay this is. So here's the carbon-14. And what kind of decay is this going on right here? This is a beta decay. All right, and you're losing a beta particle. So you have a neutron getting converted into a proton and a beta particle getting emitted as well. All right, this then is more stable. And so that is why that takes place. So how do you use this? All right, so you can now take the ratio of carbon-14 to carbon-12, and we know what it is for living things, and then after death you can measure how that changes to figure out how long ago the organism died. Now there is some calculations involved here, and your book kind of gives you this one. If you are in higher chemistry, you might just kind of do some more derivation to get to this, but your book gives it to you right here, so we're just going to go from here and use it. So this is how you can find the percent of carbon-14 in a bone at a certain point after death, or a fossil or whatever, and then you can find the age of that bone. Here's just a quick picture, just to kind of to see what's going on. So here's the decay of radioactive isotope. This could be the carbon-14 or whatever one. Here's the initial size. And you can see over time, okay, here is, if it starts at 600, here would be 300, and that time right there is the half-life. So that would be 1 half-life, 2 half-life, 3 half-life, 4 half-lives. And you can see over time, this isn't a straight line, right? Okay, it kind of is not linear by any means, exponential decay here for how it goes down. So you can kind of imagine how it keeps going down. It never gets to 0 because you're always going to divide what you have by 2 again and again. All right, so going back to this equation, this is from your book, and it tells you can find the age by plugging it into this equation. Right here is what you need to know. You'll need to know the percent of carbon-14 remaining at a given time, and you'll need to know the half-life of that isotope. So for carbon-14, the half-life is given here. And you can do this same equation for other radioactive isotopes as long as you know the percent of bone decay, or of decay, and the half-life of that. So let's plug this in. If the example that we're going to use is that there's 75% of the carbon-14 present in the bone, okay, it started at 100%. Now the half-life is when it goes from 100 to 50%. So we know that we haven't hit the half-life here, right? So the age has to be somewhere between before 1 half-life, right? So between 0 to 1 half-life. Let's actually plug it in and solve. All right, so age equals negative 2.303 times the log of the percent carbon-14 remaining, which we are told is 75% for this problem, divided by 100. And you take the log of that ratio right there, times the half-life, which we're told is 5715 years, all divided by 0.693. Work that out on your calculator. Why my numbers are off there. Work that out on your calculator, and I get an age of 2,373 years. If I'm going to think about sig figs, we had about 2 sig figs there and 75%, so I'll just say 2,400 years old would this bone be. So not too bad. You can then, and that makes sense, right? We didn't quite hit a half-life of 5,715 years, since 75% of it is still present. Here's the last question I just want to leave you with, trying to get you to think. Can carbon-14 dating be used to find the age of a fossil that, you know, you kind of estimate to be around 1 million years old? Would that be possible? And one of the things you want to think about is you want to compare kind of your estimate age of the fossil to what the half-life is. You want to choose an isotope that is kind of close to the, that has a half-life that's close to the age of the object. And here's why. If you have an object that you think is around 1 million years old, and you're using carbon-14, whose half-life is not near 1 million, okay, this is 5,715 years, how many half-lives does this decay to total in 1 million years? So in 1 million years, how many half-lives does this decay? So if you take 1 million, 10 to the 6, divided by the half-life, 5,715, you end up with, this would undergo 175 half-lives. Now, if you look at this picture up here, you can see it gets pretty small pretty quickly. If you have to go through 175 half-lives, you would not have enough carbon-14 left in this fossil to actually be able to measure. So that is the reason why you kind of have to find an isotope that is closer to the age of the fossil, that has a half-life that's closer to the age of that fossil. All right, do some more practice with half-lives. Make sure you understand some concepts there, and we'll come back and finish up with one more video.